Okay, so welcome everyone, and thank you for joining us today for this webinar on how to make your tire noise prediction smarter with acoustic simulation. My name is Romain Botton, I'm the Actran Product Marketing Manager, and I'm very pleased to be virtually with you and guide you through the following agenda of today. So we'll start by reviewing the context and challenges around tire design, in particular with respect to the new automotive market trends and upcoming regulations. We will then review together how tire noise assessment using acoustic simulation can be performed and help you to make your process smarter and more efficient. This will be actually illustrated through a series of case studies revealing the different analysis type you can do. And we'll then conclude this presentation and open the Q&A session. So during the webinar, do not hesitate to type your question in the dedicated panel of the WebEx interface, and we will answer them later on. So let's start by reviewing the context and challenges. Well, actually, tire performances can be ranked according to a magic triangle, considering fuel efficiency, wet grip, and noise level. This is very well reflected in Europe, for instance, where when you buy a tire, you will find attached to it a label providing you with insight on how performant it is with respect to these three criteria. So now the question is, how can we design a tire having the best-in-class performances? What are the challenges we need to deal with, and therefore what are the solutions offered to us to make our tire design smarter? Well, as for every object that is built, it is built out of material. So the selection of material has a tremendous impact on the final performances. When it comes to tire, they are made of multiple materials, including rubber reinforced by carbon and silica, synthetic polymers, textile, and steel. So understanding how these different materials behave and act together is typically what you can do using the Digimat solution from Hexagon. Now, once the material have been selected, we can assess the tire performances themselves. This is where simulation helps to predict grip and structural deformation of the tire in multiple scenarios. Of course, the objective is not to design a tire that will be by its own, but to design it so that it leads to good tire dynamics and vehicle dynamics performances. So predicting these performances can again be assisted by simulation using, for instance, ADAMS, and further in virtual test drive, where real scenarios combined with vehicle dynamics can be simulated. From tire performances and vehicle dynamics prediction, noise prediction can be performed. These include isolated tire acoustic signature to exterior and interior noise prediction. These last 3 points are today's focus, with a particular attention to the tire acoustic signature and exterior noise prediction. But why acoustics of tire is so important nowadays? First of all, because tire contribution to the exterior noise is very significant and is actually driving the overall exterior noise at each vehicle speed. Now, with the increased attention of noise pollution, ranked as the second major pollution source in the world, pressure to reduce vehicle noise is increasing. And this is somehow reflected in the way vehicle pass-by noise is measured. It is expected that tire contribution to the total pass-by noise will increase in the near future, reaching up to 61% of the total noise by 2024. Finally, the rise of electrical and hybrid powertrain changes the acoustic sources and the signature of vehicles, and further emphasizes the tire noise. Now, if we have a focus on the electric vehicle noise sources, well, we know that the electric engines themselves create new noise sources based on complex phenomena and need to be studied. Electric vehicles are also associated to high-tech cars, increasing the passengers and customers' expectation, in particular when it comes to sound quality expectation. On the exterior noise side, well, having a total noise level that is decreased is actually impacting the pedestrian security, making electrical cars a menace for them, particularly true at low speed. And finally, the remaining noise sources that were previously hidden are now dominant and potentially annoying for the driver experience. And this is where we also find the tire noise. So focusing on the electric vehicles and the adoption rate of these technologies, we can isolate three main barriers to their adoption. And actually, the second most important barrier is the range limits. This barrier is directly related to the energy consumption. And we know that is impacted by different parameters, such as operating temperatures, vehicle mass, but also by the rolling resistance of the tire. Lower rolling resistance implies less dissipated energy and thus a longer usage of the battery charge. And this is why we see nowadays new design of tires arriving on the market. New design induce new dynamic behavior and therefore new related acoustic signature. Having said that, let's review the different generation mechanisms of tire and road noise. Well, actually, those mechanisms are complex and involve multiple physical phenomena. The tire tread impact occurring as the tread hits the pavement can be compared to a small rubber hammer hitting the pavement. This impact causes vibrations of the tire and therefore noise radiation. The induced vibration deflects the tire, and the vibration waves can propagate in the tread band and radiate from the tire carcass itself. Now, the road texture as the tread pattern drive the repetitiveness of the impact and can change the character of the sound. In addition, the slipping and sticking of the tread blocks with the road can happen during the distortion of the tire and the appearing of significant horizontal forces. So these two mechanisms can also induce noise and vibration. Air displacement related to the rotation of the tire around tire turbulences around the tire and air pumping inside the tread can also create aerodynamic sound. And actually, in many cases, the noise generated at the tire pavement interface does not radiate efficiently by itself, but is actually amplified by three main phenomena. Helmholtz resonator and pipe resonator created by the tread passages in the tire contact patch. And finally, horn amplification due to the geometry of the tire above the pavement that enhance the sound created near the throat of the horn. But as we already mentioned, a tire is not an isolated system, and its purpose is to be integrated inside a complex environment that a vehicle is. So therefore, in order to achieve the best performances possible, we need an holistic approach. This approach should include the three pillars driving the tire and road noise generation and propagation mechanism, meaning the tire properties, the vehicle geometry, and finally the road aspect. These three pillars will impact the tire-road interactions, the related sound radiation, and finally the sound propagation. Now that we've understood the context, challenges, and the different tire road noise generation mechanism, let's review how you can make your tire noise prediction smarter with acoustic simulation. Actually, two main methodologies can be used to understand and assess tire acoustic signature. The first one consists in a simplified noise source modeling. So starting from a tire geometry, an acoustic exterior analysis, and the definition of local acoustic sources can easily be set up in Actran. The resulting acoustic radiation can already help you to gain knowledge on impact of tire deformation on horn effect amplification, understand the impact of tread geometries on acoustic signature and directivity, for instance. Vehicle geometries can also be considered, and first optimization of vehicle acoustic treatment can be performed, as well as their impact on the pass-by noise level. Another and new process in Actran involve this time the tire vibrations as the source of the acoustic radiation analysis. This time it requires an additional input coming from other CAE tool and lead to a more precise evaluation of the tire acoustic signature. The analysis setup and related post-processing remain the same, and previous model coming from the first methodology can be reused and enriched with now a more accurate noise source modeling. In the first time, I would like to focus on the horn effect and review together its impact on the tire acoustic signature. We know that the tire rod geometry actually creates a shape of a horn able to cause this larger radiation efficiency compared to a scenario where the tire is radiating in free field. So to illustrate this phenomena, we've taken two tires geometries corresponding to one single tire but submitted to two different loading conditions. In terms of acoustic model, one acoustic source is located inside the created horn, and a series of microphones are located aside and in front of the tire to assess its acoustic radiation. So if we look at the results, well, we can observe an increase of the sound pressure level record over the microphones as the frequency increases. And this is the typical behavior we expect from a horn geometry. This is further highlighted when we look at pressure maps and pressure isosurface, looking at the side of the tire and at the top, where we can clearly see the impact of the horn effect, increasing the sound pressure level close to the tire and therefore in the far field. Another interesting phenomena to study is the impact of the treads geometry. So we know that tread passages of the tire in contact with the road can create acoustical system able to enhance the sound generation. So in this scenario, we have taken two tire geometries with different tread pattern. When we look at the contact patch created by those two tires, well, we have two different print geometry. Starting from those print geometry, we have defined a series of acoustic sources inside the tread in order to represent typical excitation that can occur inside those acoustical systems. In addition to this configuration, we have also created asymmetrical configuration where we would like to assess what will be the effect of a non-homogeneous contact of the tire with the road, and therefore a non-homogeneous distribution of the acoustic sources inside the tread. As we can see on the current slide, well, the tread geometry has a major impact on the acoustic directivity. Furthermore, a non-uniform acoustic loading also significantly changes the acoustic response of the system, sometimes increasing the acoustic radiation in some direction. Now, if we zoom on what is happening inside the acoustic channel inside the tread, we can highlight, thanks to Actran post-processing capabilities, the acoustic resonances occurring inside the channel. This is easily visualized by looking at acoustic intensity vectors. And in this case, the asymmetrical loading condition enhance the acoustic resonances that can occur inside those tread geometries. Now, let's have a look at the second methodology using tire vibration result. So tire vibration result can be obtained from a steady-state tire rotation analysis or transient rolling analysis. And since Actran 2020, a new mapping tool allows you to map these results onto a stationary finite element mesh. It is also possible to ask for an automatic generation of the tire finite element mesh deformed based on time domain results. And thanks to its unique mapping technique, different tires surfaces can be handled, including slick, grooved, or threaded tires. So once the time domain result have been mapped on the finite element mesh, this result can be used to perform an acoustic radiation in time or frequency domain, including acoustic dissipation mechanism inside the thread, for instance, or also in situ performances considering acoustic treatment and Rho absorption effect. Pass-by noise prediction can also be done inside the same computation. So having a deeper look at this process, well, we know that we start from time domain displacement in a moving reference frame. From those results, well, we map them in a fixed reference frame. A DFT can be performed in order to move from time domain to frequency domain radiation analysis if we want. And also, as previously mentioned, the user can output the deformed mesh, post-process it, and create inside Actran user interface the acoustic mesh around. So once these operations are done, acoustic radiation in time or frequency domain can be launched. And again, this is a new capability since Actran 2020. Now, let's have a quick look together on the acoustic mesh creation inside Actran VI based on a deformed mesh output. So in this video, what we are doing is importing a deformed mesh. And again, this deformed mesh can be automatically computed by Actran or output by another software. Starting from a 3D mesh, we simply create a 2D skin out of it using Actran meshing tools. And what we will do is actually remove what we don't need, meaning what is inside the tire, as we are interested in the acoustic radiation around it. Fill the tire side, so we create a closed system. Once this is done, now what we will do is focus on the contact patch, and remove what we don't need. So to do so, we will select elements that are connected together and simply delete them. Now, in order to make sure that everything is aligned with the road, we use the align function in Actran and align all the nodes from the whole on the same plane. Once it's done, we simply split all the quad element into triangle ones. And now we have a closed mesh aligned with the road that we can use to create our exterior acoustic mesh. So this exterior acoustic mesh can be created inside Actran VI, or you can also let the solver do it for you during the computation and combine this mesh creation with mesh adaptivity, meaning that the mesh that the solver will create will always be adapted to the frequency you want to solve. But here what we are doing is just illustrating what the solver will do actually for you, meaning starting from a 2D mesh, create the volume mesh around it. As we see here, when we cut the mesh, we see that we have created a connected 3D volume mesh that represent the acoustic surrounding around the tire. Now, I'd like to review with you a case study analysis. And actually, in this analysis, tire vibration from a time domain simulation are used as an excitation for an acoustic radiation. This acoustic radiation will be performed in different environments. First, we will perform a semi-free field radiation, and in a second time, analyze the in-situ effect with and without acoustic treatment on the wheel arc. It's also the opportunity for us to present you how you could perform efficient parametric and optimization analysis of such acoustic treatment. And finally, how to assess the pass-by noise still remaining completely in Actran. So looking at the total acoustic radiated power from the tire, quantity that is directly output by Actran at the end of the computation, it is interesting to understand the sound directivity. And for that, in this analysis, we have created arrays of virtual microphones that are located around the tire and isolated 4 frequencies for deeper analysis. So if we look at the directivity of the tire according to the different microphone arrays, we can highlight the ability of the tire to radiate more at a lower frequency while observing a more complex acoustic pattern as the frequency increases. Higher frequencies peaks are typically driven by the tread pattern and the rotation speed of the tire that induce high order mode vibration of the tire structure. In this particular case, we can observe also that this mode can efficiently radiate acoustic noise. Now, what is interesting is that based on exactly the same model input file, we can easily include a complete vehicle geometry around it, provided that you have a finite element wrap mesh of the vehicle. And therefore, you can study the effect of the vehicle geometry on the acoustic radiation and observe that those effects are not homogeneous over the frequency range for the selected array of sound at some frequency, while it's also able to enhance the acoustic radiation. We can also, based on the same model, add acoustic treatment effect. So what you see on the right-hand side are typical locations for exterior acoustic treatment. And those treatments can easily be added using Actran poroelastic material modeling capabilities. So a common method to do so is to use acoustic admittance boundary condition applied on 2D surfaces. And in the following example, well, we used the absorption coefficient acoustic treatment boundary condition that is applied on the wheel arc surrounding the tire and uses a frequency-dependent value. Actually, the same technique can be used to model road absorption properties as well. Now, what's its impact on the acoustic radiation? Well, as expected, we can see that as the frequency increases, well, the acoustic radiation is more and more impacted by the presence of acoustic treatment on the wheel arc, and therefore the sound recorded over the virtual microphone is decreased. This can be further visualized using acoustic maps, where we see on the left-hand side the no acoustic treatment configuration, and on the right-hand side the configuration with acoustic treatment. We clearly see that around the tire and inside the wheel arc, the sound pressure level is reduced thanks to the acoustic treatment. And it's also impacting the sound pressure level in the far field, as we see on the directivity map on the bottom of this slide. Now, how can we perform efficient parametric study and optimization of acoustic treatment? Well, imagine that you have different materials that you would like to bench. Well, a typical and conventional approach would be to take your model, define here on the red surfaces acoustic treatment, and if you have several material to test, perform several iterations where every time you have to relaunch your model and therefore perform a complete computation. Now, in Actran, what is available is what we call the static condensation approach. In this approach, what we do is first reduce the model over a set of surfaces where we know that the boundary condition will change. And what we do is compute the static condensation of this model over those reduction surfaces. At the end of this step, we create a condensation database that can be seen as acoustic superelement. And once we have created this condensation database, well, we can reuse it over the different iteration. What is very interesting with this numerical technique is that as soon as you start to make more than one iteration, you directly have a gain in terms of computation time. This is highlighted on the left-hand side of this slide, where we compare the time for one computation versus the time of the computation using the static condensation method. And we see that in this particular case, we could gain up to 60% time. In addition to computation gain in terms of time, we also have a constant memory over the frequency, with therefore a reduction of the memory used and required when solving higher frequency cases. I'd like to just recall why we see a progression in terms of computation gain, and we have this stairs behavior. It's because in Actran, we rely on mesh adaptivity, where actually the solver is meshing and remeshing the acoustic volume mesh for each frequency, meaning that we don't have one model to solve over the frequency, corresponding to the red curve that we see here, but actually we have several meshes always adapted to the frequency that we are solving, and therefore reducing the total time of computation. This is a comparison also of computation timings, where we are using only one single CPU versus the parallel capabilities and the scalability of a solver, and we are able to reduce the computation time from 10 hours to 1 hour and 10 minutes. Now, in coming back on our scenario where we are comparing different material applied on a wheel arc treatment, I'm referring to one of the publications we did last year together with Autoneum, where we were comparing 3 different materials. One plastic that has an absorption coefficient that equals to 0, and 2 different felt having different absorption curves. The purpose of the study was to assess the efficiency of the static condensation method, and also assess the impact of the acoustic treatment on the final pass-by noise curve. So as we can see on this graph, well, obviously the plastic has lower performances compared to absorptive felt that have the best impact on the pass-by noise level. Still, in this case, the impact is quite reduced, simply because the location where we have put the material is not the best one in terms of wheel arc acoustic treatment. Well, it is recommended to put them more in front and behind the tire instead of the top of the wheel arc treatment. Now, how actually can we simulate the pass-by noise in Actran? Well, we know that in finite element simulation, it's quite complex to represent a moving vehicle like in the standard measurement procedure. So instead of having the vehicle moving and everything around fixed, we are doing exactly the opposite. So the vehicle is still, and we consider that everything around is moving. So this is strictly similar to what is done during indoor pass-by noise measurement. So the noise radiated by the different sources is evaluated on 2 arrays of microphone located on each side of the vehicle, and the pass-by noise signal is reconstructed by assembling results from the different microphones. So since Actran 2020, a new post-processing component is available and is related to acoustic radiation, dedicated to automotive industry, and dedicated to car pass-by noise output based on IEC 61672-1 norm. So with these new post-processing capabilities, well, users need to provide information related to car length, car speed entry in the test track, acceleration, if any, and speed out if needed, as well as the distance in between the car and the microphone. So based on this information, well, virtual microphone will be created automatically during the computation, and the overall sound pressure level as function of the time or vehicle position on the test track are automatically computed and available through a new dedicated post-processing indicator inside the PLT file. So these new indicators are available for simple acoustic sources like monopole, or even more complex sources modeling using BC mesh excitation, and therefore tire noise radiation as well. Now, I'd like to come back on the tire acoustic signature and a method for noise reconstruction that is actually a solution for data exchange. So the idea of this method is to reconstruct the overall noise sources of an isolated tire from experiment or simulation in order to exchange tire acoustic signature information in between, for instance, tire manufacturer and OEM. It provides more complex noise and once you have reconstructed these sources, well, you can assess the noise propagation simulation in a more complex environment, for instance. So how it works? Well, for instance, we can place two monopole at the side of the contact surface at a certain distance. And the idea would be to minimize the difference between reference pressure obtained from measurement or from more complex simulation and the radiated pressure obtained by those two monopole. At the end of this optimization, you will get source amplitude and phase shift for those two monopole that would create an equivalent acoustic radiation or measurement or more complex noise sources. So this is a good solution and easily done in Actran in order to create an acoustic field that corresponds to what you have measured and exchange this information with other partners such as OEM. Once those OEM have this information, they can use this information inside their computation and consider vehicle geometries around it and therefore optimize acoustic treatment. So this type of study has been already performed by Autoneum and Chalmers University, and you can find a reference to this paper on the bottom of this slide. Now, coming back on the integration of tires in vehicle design, we know that we have several industry pain points, and one of them is to retrieve the exact geometry of the vehicle. Well, actually, to do so, you can use hexagon scanning solution to scan a real geometry of a vehicle and create out of it file that can be used inside your acoustic simulation. This scanning can be done for a component, but can also be done for at full vehicle level. And once you have retrieved this geometry, you can use them as an input inside your acoustic simulation, for instance. I'd like also to take the opportunity of this webinar to recall that thanks to scanning capabilities of Hexagon, you can scan real environment and perform your dynamic simulation inside an environment that has been scanned. So what you see here on the video is a truck moving in a real environment, or at least a virtual environment based on data scanning, and where an ADAM simulation is used to assess the dynamic of the truck inside this environment that has been scanned. Now, of course, if we come back to noise, well, we can perform road noise or interior road noise prediction, starting from information on interaction in between the tire and the road, and you know that they create excitation that can propagate through the chassis and therefore create noise inside the vehicle. What we see here on the slide is an highlight of the work we have performed together with Audi and published at an ACA conference 2 years ago, where we were optimizing the acoustic treatment on the floor of the vehicle in order to minimize the sound transmission through the floor due to road noise excitation. So it's time to conclude this webinar. So we have seen that assessment of tire noise becomes mandatory for both exterior and interior noise management due to new regulation, and in particular regulation following the importance of a decrease of noise pollution, and due to new vehicles architecture. We know that Hexagon provides an exhaustive set of solutions for tire noise prediction, including simple noise source modeling, vibration result mapping, available since Actran 2020, noise source reconstruction, that is data exchange in between tire supplier and OEM. You can also easily perform in-situ prediction, including pass-by noise assessment and external acoustic treatment optimization. And we know that we also have a solution for interior comfort noise prediction, resulting from dynamic load excitation or exterior acoustic noise sources. I would like to conclude this webinar with this quote from Nietzsche: "Without music, life would be a mistake." And we want to be beside you in order to make your life easier. So thank you very much for your attention. And now it's time for the Q&A session. So would you have any question? Please type them